So today we will start on data link. So basically, like so far we were seeing physical layer where all the electrical characteristics, like from analog to digital conversion, and like what are all the, I mean, whenever I want to transmit data from TX to RX, so how the data encoding scheme should be in the transmission media, right? Wired or wireless. So we were discussing majorly on line coding aspects and like bandwidth, frequency, all are physical properties. So in the data link layer, okay, so is one layer above the physical layer. Okay, the responsibility of data link layer is mainly on the addressing, okay, addressing, flow control, error control, and media access control. Okay. So actually, I mean, see, when I say I want to transmit and receive at receiver end, so it won't be one-to-one communication, right? So if you consider the case of internet, so your packet will be sent to network, and that packet has to properly route into the destination address, right? I mean, it will pass through various nodes like the network vendor, and like from there, like see through C cables, and like if, for example, if I'm sending a message to a client in US, so then it will pass through various nodes, various devices. So when that packet reaches these various nodes, so it should be properly guided, right? So for that we need addressing and flow control, right? We should define how the data should transfer and like what is the address for that. And when it transfers, so always like I mean, when it transfers, actually like there will be possibility of noise, and due to that, like bit error may occur, and your packet may get corrupted. So that error control mechanism also we should have, right? And the accessing part, so when it actually transmitted through that way, how we deal with the media access. Okay. So this basically in the data link layer, what we are doing, the stream actually from see actually in the OSA layer, above data link layer is network layer, below data link layer is physical layer, right? So from network layer we get stream of data. So for example, I have like 50,000 bits, so I'll just get that raw 50,000 bits. Okay. So um, so, but actually, when I say that like 50,000 bits I receive, uh, that actually it will convert that raw data to frames. Okay, so the physical layer so that it can manage properly. So chunk of data it can send, right? I mean, if I get like continuously keep on sending the data, I mean, it is very difficult to handle. So it will packetize the things. So it is something like, let me consider supermarket scenario. So when they want to actually like they might get like big bag of rice, so that like they'll packetize into manageable packets of 1 kilo or 2 kilo, that like user easily can pick that package, right? So same way here, he actually get full chunk of data, the huge set of data, so he will packetize, so it can at the receiver end, user easily can handle and understand that data. Okay. Yes. And for example, when I say that like it is like packetizing as a 8-bit, okay, 8-bit, it adds some headers. In the sense, it adds address. I was saying about this, right? Some address, flow control related information, and error control related information. So it is going to add it in the, so that 8-bit plus these data will be added here. The flow control related data and um, header related data. Okay. So if the rate at which data are absorbed by the receiver is less than data at which data produced by the sender, then the data link layer imposes some flow control mechanism to avoid overwhelming the receiver. In the sense, so you say that like my EX data rate is 10 Mbps, okay, and RX data rate is just 8 Mbps. So if I say, transmit at this rate, the RX will actually we will be in the confusion that like he cannot handle this huge amount of data, right? So what we do actually, this data link layer he controls. I mean, he may reject some packets. He may impose some kind of like if there is any um, what to say repetitions, so that he may remove some kind of flow control. He does. Okay? And data link layers adds reliability to the physical layer by adding mechanisms to the uh, mechanism to detect and retransmit damaged, duplicates, or lost frames. So, for example, if this frame what I sent, if it is lost, then it will add some mechanism so that like same frame it will be sent again. So that like see now when I say that like same frame has to be sent to again, then like it should have some memory, right? So it should have some kind of buffer so that like it will wait for some time. If that it gets to know that like that data was corrupted, he will just resend it. So after that he may ignore that like whatever he stored in memory. I mean, if it reached successfully, he will ignore that. So next actually important thing what we want to discuss is how it does error control and detect error controlling and error detection. This one. So whenever we transmit, actual expectation if I send like a number 8 from the transmitter, so it is expected that like at the receiver also what we receive it is 8, right? That is accurate data. But when the data we transmit from one node to another node, uh, due to noise or maybe like due to faulty network, due to damage in the cable or channel, it will get corrupted, right? So we should have a mechanisms that whatever we made that error, so at the receiver end, so it should have a proper knowledge that whatever I have received that is like erroneous. So that kind of mechanism we should have. So we will see what types of error it can occur. Types of errors. First type of error, it can be single bit error. So I can give you the screenshot of that. You see here, I transmitted 0 0 0 0 0 0 1 0. That is 2, right? 0x. Where the receiver, if you see that 0 changed to 1. Instead of 2, it became 0x a. Okay, so this is due to single bit error. This is one type of error what it may occur. So if it is like more than one bit of error, second type of error, more than one bit of error, that we call it as burst error. More than one bit. You see here, I transmitted 0100100010000011. If you see like more than one bit got corrupted, kind of burst error. Okay?
Yes.
So in order to avoid this kind of error, okay, so what we do basically we add redundancy.
Hmm. Yes.
The meaning of redundancy is, what is the meaning of redundancy? So we actually send some extra bits, redundant bits, okay, extra bits. We send extra bits for correcting or detecting the error. Okay? So usually, not only in data communication, we have another subject called information theory and coding. In that also, information theory and coding is completely on this error detection and correction. So usually, when we talk about error, right, we deal with two types of things. One is error detection, and another is error correction. Okay, these are the two important types which we usually deal. So in the detection, what we do, we can just detect. I mean, like if you have on this error, so error detection technique, he will just detect. He doesn't have a capability to correct it. Whereas error correction coding, he can also correct it at the receiver end without depending on transmitter. He can just independently correct it. These are the two types of um, mechanism. Okay, the correction of error basically is more complex than detection of error, right? Yeah. So actually, in case of detection, if for example, if the receiver detects some error, right, he cannot correct it, right? As I said, it cannot correct, but he will tell the transmitter that I detected the error. So if the transmitter gets to know that he detected the error, then he will retransmit. Retransmit. So this is the retransmission mechanism. In the another mechanism, we have something called forward error correction, FEC, forward error correction. So here what he does, if he detect any bits are erroneous, then he will correct by himself. Okay.
Yes, sir.
So let's see the error correct detection mechanism. If you see here, he has k bits of data at the transmitter. So he will generate some error detection mechanism. Actually, will generate some error detection bits. Based on that, k bits is converted into n bits. Okay. So for example, this is generating some a bits. A plus a will become n.
Yes.
So here that n bit is received and he will discard a bits, and here finally we get back.
Yes. Yes.
Here we detect the error.
Yes, sir.
So for error detection or correction, we usually use one arithmetic called modular arithmetic. Modular arithmetic. The meaning of modular arithmetic is, so if we say I want to have some counter with the modulo n, okay, then my counter value will have, like, that system can have number from 0 to n minus 1 only. Okay, if I say I am dealing with modulo 4, then in that system I can have 0, 1, 2, 3. Okay, again if I get some number called 4, then again modulo 4 will become 0. If I get number 5, then it is 1. Number 6, it is 2. Number 7, it is 3. Number 8 is 0. So in this way it will keep on proceed. Getting?
Yes.
This is modulo n system. Okay. So actually this why we are discussing is like the coding scheme we have to understand, right? I mean, I said like here is one generator, right? The data
Yes.
word generator. We have to understand the architecture, what is there inside this generator. So for that we need these arithmetics. So next arithmetic what we deal is actually XOR gate. XORing. Do you know what do you mean by XORing? If I have A, B, number bits are 00, 01, 10, 11. Can you tell me what is the expected Y?
0 is one. I'm sorry.
Here it
One,
is 1,
one,
1.
0.
Next, we will see various coding schemes. Okay, for like error detection and error correction. What are the different coding schemes are available? First scheme, what we deal is block coding. Okay, block code. So here, whatever the message we get, okay, we divide that message into k bits. K bits message. So my, even if I get some n number of bits, out of that I will take k bit, kk bits chunks I will form. So this k bit I will call it as data word. Is this clear?
Yes.
Okay. Then to this k bit I will add r redundant bits. R redundant bit. So my final message size now it became n equals to
Yes,
k
sir.
plus r. Right? So this is actually whatever initially we had k bit, that is a data word. Now this k plus r became code word.
Yes,
So
sir.
you can see this mechanism, right? K I shown you, instead of r I said a, right?
Yes, sir.
So for each data word we have corresponding code word. So here actually I can show you some example. I mean, it need not be same, it can be different also. So I can show you one of the example. I have data word and I have So I can have possibly 2 bits. Let's start with 2 bits. 00, 01, 10, 11. Okay. Code words will become 000, 011, 101, 110. Okay. So if I want to send 01, then the code word is 011, right?
So this code word, like, it's based on XOR.
And
It's 00, code 00.
correct. It is XOR of these. 011, 101, and 110. Actually, XOR of this. So this is actually one of the examples. So it need not be same. So it can be different also. Okay. So this is right now one code word scheme where they actually XOR these 2 bits and they will add at the end. Okay. So this we call it a cyclic redundancy code. Okay. So if it is 01, we send 011, right? So at the receiver end, for example, if I receive 011, then it is correct. It is error is not detected. If I receive for 01, if I receive 010, then something went wrong. Correct? This way actually we detect the error. Clear?
Yes, sir.
This is actually block coding mechanism. See here, like only 4 valid coding schemes we have, right? Here. So
Yes,
000. So for example, if you receive something like 001, then this is not a valid scheme, right?
yes,
Same
sir.
way we don't have 111, right? Then this combination, if it receives, then we can say it is an invalid combination.
Yes.
So one thing you should remember, let me just from this table itself we can make out that statement. So even though you have in the data words, you can have, if it is k bits input, you can have 2 to the power k different data words, correct?
Yes, sir.
But code word wise, 2 to the power n code word also need not be valid. Okay? Out of that, only 2 to the power k will be valid. Hope this statement makes sense, right? You can see here we can have 7 combinations: 000, 001, 010 is also not valid, correct? So for the 2 to the power k is actually, for example, k is 2 here. For the 2 to the power k, that is 2 to the power 2, 4 data word, 4 code word only valid. Out of 2 to the power n is actually 2 to the power 3, that is 8. Out of 8, only 4 code words only valid,
Yes, sir.
right? So that makes sense, right?
Yes, sir.
One second. So next, actually, one important concept we will study about Hamming distance.
Yes.
So this Hamming distance we usually use for error control coding. Okay? So it's basically like at the receiver end, if you want to correct the code, for that concept we use Hamming distance. So here, um, so basically what we do, right? So we have, you assume you have two words, two data words of K. Yeah, I have one chunk of data of K bit, and I have another chunk of data of K bit. Okay. So the Hamming distance between these two words is the number of differences between these two words. Number of differences between these two words. In the sense, if I consider 10111 110111, if you see here, let me consider 1. Uh, let me make this as 0. So now if you consider 1 1 same, here these two bits are same, and this third bit also same, fourth bit also same, fifth bit is different, right?
Yes.
And sixth bit is same. So the distance only one bit is different. So the Hamming distance is 1.
Yes.
Okay.
Yes, sir.
So if you have two words, okay, x and y, then Hamming distance between those two words we show it as d of x comma y. This is the Hamming distance between two words. So easier way to find this, right, Hamming distance, we XOR these two numbers and we have to count the number of ones.
Yes.
Ones. So here itself, if I XOR this, everything will get 0, and wherever there is a difference, I'll get one there, right? Then count number of ones. So if it is 0, then we won't call it as Hamming distance. Always Hamming distance has to be greater than 1. I mean, if the numbers are same, then we cannot say that, like we can find the Hamming distance. That is just two numbers. Okay.
Yes.
And when you have n different code words, in that, if we want to find the Hamming distance, right? Then like we have to find Hamming distance of all the numbers, between all the numbers, and minimum of the Hamming distance between them we have to find.
Yes, sir.
You're getting, I mean, for example, let me consider I have code words like 01 10 11 and 00. Okay, so here Hamming distance between these is actually 1. Distance between this is 1, right? Between
Yes.
these is actually 2, right? 1 1 to 0 0, it is 2, correct?
Yes.
So even though we have 1 1 1 2, so minimum of these Hamming distance, so in the 2 bit data words, Hamming distance will be 1. Okay, because d minimum of all this Hamming distance will be the Hamming distance of that particular coding. Clear?
Can you explain once?
Okay. So there are two things in Hamming distance. You can have Hamming distance between two code words. So this word and this word. Okay. This whatever number of difference of ones you get, that is actually Hamming distance. But whenever you are whenever someone asks what is the Hamming distance of entire coding scheme, okay, so you have to find the like possible all the possible coding in that coding scheme. You have like you assume that like 0 1 1 0 1 1 0 0, these are the possible code words. Okay, so here various first you have to find the Hamming distance from these two others. So from here to here 1, here to here 1, here to here 1, correct? And distance from this actually these two others, so 1 1 1 from these two others. So 1, here it will be 2, then rest all 1 1 1, right? So then even though get 1 1 1 1 and 2, so the Hamming distance is minimum of all the series. You got it, right? So you got actually like 2 1 1 1. So you even though you got 2 as the Hamming distance in one of the case, the minimum of all this, that is 1. Next, we talk about linear codes, linear block codes. So here what we do, right? We take two code words, code word 1 and code word 2, and we XOR it and we get one output that is actually another valid code. Okay. So this is actually linear coding mechanism. So we take two code word, so we XOR it, we get another code word. That is the linear coding scheme. Okay? So another type of coding scheme is actually parity checking code. So here, here what we do basically, here what we do is actually we feed, for example, we have like assume you have k bits of code. Okay? These k bits of code we convert into n bit of code that we checked, right? Initially one mechanism, that mechanism. Okay? K bit of code basically we are converting into n bit of code, and the n is nothing but k plus just one bit by XORing all the bits, right? XOR, you have to XOR all the k bits and you get one bit, right? So that is nothing but extra one bit. That is actually we call it a simple parity check, linear block code and simple parity check. This extra bit what we get, that we call it as parity bit. Okay. So we will just I'll show the block diagram of a simple parity checking code scheme. So if you see here, I have a data words. So I will XOR everything. Generator is nothing but I'll be XORing it, right? So if I have 4 bits, I will XOR the new bit what I got. It is a parity bit. Then I will transmit. When I transmit, I'll get like receiver bits B2, B1, B0, and Q0. Again, what I'll do, I'll XOR these bits, these 4 bits. Okay,
Yes.
and I'll get one bit, right?
Yes, sir.
Syndrome bit.
Yes.
That has to be equal to this bit Q0. Correct?
Yes, sir.
If it is equal, then I don't have any error.
Yes, sir.
I can consider that data word. If there is not matching, then I have to discard it.
Yes. Yes, sir.
So why it is unreliable channel? Any transmission line is unreliable channel. We don't know what kind of noise may occur, what kind of disturbance may occur. Don't know. Correct?
Yes.
Take one problem. Let us consider sender sends the word 1011. Okay. The code
Yes.
word is created from this data word is 10111,
Yes.
which is sent to the receiver. Okay. And if we don't have any error, so at the receiver end also what we get?
One, sir. One,
10111.
one. Yes,
Okay.
sir.
So if for example, due to error, a single bit got changed, A1 got changed, we received 00111. Then if you XOR it, 000011110.
Yes.
Correct? This is not matching. What happens?
Yes.
Discard.
Discard. Yes, sir.
So for example, this R1 itself is corrupted. Then what will happen? 10110 will happen. Correct?
Yes.
Again 10111100111. So not matching. Discard.
Yes.
But here one risk is there always in error detection coding, right? Risk. This can detect only one bit of error. For instance, you assume 0011. This is a wrong code word detected. And also R1 also, the parity bit also got corrupted. So then it will consider this word, right?
Yes.
That kind of risk is there in the error detection code. That's where like more reliable will be error correction codes.
Correction. Yes, sir.
And not only one bit, this can detect any odd number of bits. Odd bits. Here even bit of error detected. But like again 2 more bits corrupted, right? So 3 bits are corrupted. Then again it will say it is error. So I cannot say like only one bit. Any odd number of bit error is there, then it can detect.
Yes, sir.
Okay. Okay. So tomorrow we will see little bit on two-dimensional parity check. Then
Yes,
we
sir.
will see something called CRC polynomials. I think that completes, okay. CRC polynomials completes this data link layer. Okay.
Yes, sir.
Then we will start network layer.
Yes.
You have another month for the exam, right?
Yes.
Okay. And
Okay.
oh, I mean, tomorrow second unit will be completed within a week. I mean, once this data link layer will be little lengthy. After that, network layer and all we can.
Yes, sir. So can you solve the question 10 seconds? It's like they'll give problem
Yeah, yeah, sure. You have shared me those.
question.
Right?
Yes, sir.
Okay, not today.
Uh, yes, sir.